Okay, this is a quick video to help guide you to prep for Exam 2. Exam 2 is on Chapter 2 of the book, The Law of Running. And we covered Chapter 2 starting in week 4, and we continued that into week 5. All right, so these are the videos that will be emphasized in lecture content for the exam, which will happen during week 6, which I start to cover chapter 3. But only chapter 2 is going to be covered on the exam. All right, so let's see. Let me bring over the terminology worksheet that I've already posted on Web Campus. You can go back and look at this. And here's chapter 2 terms. This is not all inclusive, but these are definitely terms and concepts that you want to be familiar with going into exam 2. You want to know what air is. We're breathing air. What percent of air is oxygen, that part that we need for aerobic conversion of chemical energy to mechanical energy, or to ATP in this case, that we go through the energy systems. We want to know VO2 and VO2 max, and we want to understand VO2, and I'm a little lazy here. I should have the dot over the V to represent a rate of oxygen consumption. And we want to understand that right now I could measure my rate of oxygen consumption, and you should have a sense of how much that is. It's resting metabolic rate, which is around 3.5 mLs per kg per minute. And we want to understand that as I start exercising, I'll start consuming more air and start using more oxygen to transform our fuel, our carbohydrates and fats, over to ATP, which will ultimately be used for mechanical energy and shortening of a muscle, generating a force, and then either running or pushing on a pedal or swimming, what have you. So VO2 we can measure at all different levels of intensity, and the amount of oxygen used, the rate of oxygen used is going to be related to that intensity of endurance exercise. VO2 max is a single number, and I go through, and Noakes goes through the history of VO2 max, quantifying it, and discusses whether or not this is really an important parameter to understand. And we need to understand that the maximum rate of oxygen consumed is going to be a function of how much muscle is ultimately being used in the intensity of exercise. And so this VO2 max ends up being different if we're doing swimming, a swimming test, or a run test, or a bike test. But we should be familiar with a maximum effort graded exercise test. A very common test to use to assess fitness. And the fitness parameters that we will pull from this type of test will not only be VO2 max, but it may be some sub-maximal values that we're really interested in. And we'll get to later on in the semester, lactate threshold, anaerobic threshold, things like that. Those happen at the sub-maximal stages of a graded exercise test. But you should be familiar with terms like VO2, rate of oxygen consumption, VCO2, rate of carbon dioxide exhaled, respiratory equivalent ratio, the ratio of those two numbers, heart rate, and lactate that's in the blood. So I always put that in square brackets to represent lactate concentration. So we want to start being familiar with how these parameters change over a graded exercise test, and go through that in these presentations. And again, Noakes does a good job of talking about some of the classic research related to maximum rate of oxygen consumption, and talks about this idea of whether or not there's a plateau in VO2, and that plateau would indicate that a maximum rate of oxygen consumed has been achieved. So no matter if you try to run faster, in the examples used in the textbook, that maximum rate is achieved, and you can't exceed that. Noakes challenges that idea, and and I go through that in some lecture material. And very few tests actually see a plateau in VO2, even though you're increasing speed. Roughly, maybe less than a third of the tests. Now, in this chapter, he also talks about limits to endurance performance, and he gets more into the different performance models or phrasing that he uses to explain different reasons or different ideas in terms of why there's a limit to endurance performance. And he talks about the cardiovascular anaerobic model. He uses that quite a bit to sort of talk about more of a classic physiological explanation of endurance performance, especially limits to endurance performance. But it really introduces this new model, and Noakes is very well known for the central governor model. And this model is more holistic. It's more about the brain sensing different things and ultimately shutting down muscle generation of force, and therefore limiting performance. And he'll go through several different ideas in terms of what is being monitored and what may be causing a limit to performance. And he'll talk about a thermostat later on in chapter 4, that we detect a core temperature going up too high. Or later on we'll talk about a glucostat, that blood glucose levels get too low. There's other ideas. This is just a model. It's a theory. It's a hypothesis, a statement we believe to be true, or a lot of people do, based upon what we know. But the point of the central governor model is the endpoint of a graded exercise test is far more complicated than just saying, oh, muscle glucose is low. It's much more complicated than a simple physiological explanation. So we'll get into that more, and this ultimately is what we want to understand, is how to do an endurance event faster, or how to go farther in an event. So this becomes important. And then he introduces this other model, biomechanical muscle power model. And the idea with this model is not all of our muscles are created the same. And so when we start looking at different athletes, some athletes may simply be able to generate force from a muscle better than another athlete, based upon the structure of the muscle, or the pennation angle, or maybe even some of the elastic characteristics within a muscle and within a joint. And so this becomes more a biomechanical muscle power model that he refers to in terms of sort of the mechanics of generating muscle force. All right, some other things that I go over in this chapter, factors that influence VO2. And now I don't have max there, so that's influencing even submaximal VO2, or how much oxygen we're consuming to run a given submaximal pace. We're not always interested in VO2 max. You'll see that in this throughout chapter 2. And I use two terms, and I go into these quite in depth, so you really want to know how these two terms are the same and how they're unique. Running economy and energetic cost of locomotion. So running economy is how much oxygen we're consuming, the rate of oxygen consuming, the rate of oxygen that we are consuming for a given running speed. So that's a rate, okay? Energetic cost of locomotion is an amount of oxygen consumed for running a given distance. So the units of these parameters are unique, but yet they're linked mathematically. And I go through the math of how these two are linked. And because they are linked mathematically, they can be used interchangeably, but the way that you describe VO2 is the language that you use ends up being just a little bit different. So you do need to be careful when you're reading research and you see either of these terms. You want to make sure that the authors are using the same units and expressing the definition the same way as what we're going through here. I go through what I call best practice or common practice for using these terms. At the end of the day, they give you very similar information. You just look at things a little differently if you're using one term or the other. So for example, running economy tells us how fast we're using calories, right? The rate of calories being used. Energetic cost of locomotion would tell us the total amount of calories that we're using to cover a given distance. So if we know the time to cover the distance, obviously we know the rate, or vice versa. So mathematically, these are linked. But those are the ways that we typically use each of those terms, or an example of how we use those terms, to give a different perspective. I may want to know how many calories I'm going to need to cover a marathon. Or I may want to know how fast I need to convert calories from chemical state to the mechanical state. So that rate of calorie being used is just as important as the amount of calories. And so we use these terms to sort of zero in on different aspects of performance. I talk about predicting endurance performance, and this is really tough, but boy, if you're an athlete or a coach, this is what you really want to do, is to be able to assess how well your training program is developing an athlete or yourself in order to achieve the desired performance goal. And I talk about changes with aging in a pretty broad brush here. As we get older, it gets a little tougher to do these endurance performance and go through some of the reasons that Noakes covers regarding the influence of aging on endurance performance. Okay, I hope that's helpful to prep for the exam, and all the immersion videos are helpful to just get a sense of how these terms are used to understand endurance performance. So hopefully those are helpful as well, just understanding the language and the terms, and how we're talking with athletes, and how we're trying to learn more about how to go faster or further in endurance performance. Okay, thanks everyone.